OCR A-level physics. This is my first video for my playlist on electric fields. So electric fields are number one. Now, an electric field is a region of space where charges experience forces. I'm going to be doing a lot of comparisons with gravitational fields as well. A gravitational field is where masses experience forces. Here, charges experience forces. So this sphere, the Van de Graaff generator ball, is producing an electric field. Okay, or rather the charge on the ball is producing an electric field. And then on the small ball, which is on a bit of an insulating thread there, that charge is experiencing a force because it is in that electric field. Okay. Now, the strength of an electric field, we say, is the force per unit charge. If you're asked in an exam, define electric field strength, it's the force per unit charge. Now, our unit of charge is the Coulomb and our unit of force is the Newton. So E equals F over Q newtons per Coulomb. Now this equation, E equals F over Q, we can use that for non-uniform fields or uniform fields. That is the strength of the field at a point. The direction of the field at a point is defined as the direction of the force that would act on a positive charge. So if I put a positive charge at that point, the force would be in that direction, so the field is in that direction. It's the direction of the force that would act on a positive charge. Now, we can't see electric fields, but we can represent them using field lines, electric field lines, like we do gravitational field lines, or later on magnetic field lines. Now, these field lines, the arrows, show the direction of the field at any point, and the field is stronger where the lines are closer together. So looking at this diagram, I can tell that as we move away from this sphere, the field is getting weaker because the lines are getting further apart. This diagram shows the field produced by a positively charged sphere. For example, like the Van de Graaff. Yeah, if the sphere of the Van de Graaff, assume it's uniformly charged, and this would be what its electric field, how you would represent its electric field. And it's an example of a non-uniform field. Little question, how would the diagram be different if the charge were negative? And the answer would be that the arrows would be pointing in the opposite direction. Okay, now this is a sphere carrying a charge Q, and this is something that we call a point charge. Now, a point charge doesn't have any dimensions. If you think about it, you know, we know what the radius of a proton is. What's the radius of an electron? Well, there's all kinds of ideas about what an electron is, but we can think of an electron as being a point charge. In other words, it has no dimensions. It's an object, it has mass, but it's a tiny, tiny charge concentrated at a single point. Now, if you look at the two electric fields, if the charge is the same, then outside of the sphere, it's identical to a point charge. So when we're doing things like working out the force or working out the field strength, we do it to the center of the sphere. We don't do it to the surface, we do it to the center of the sphere. Look at this diagram. Here's another non-uniform field. And how do I know it's non-uniform? Because at certain places the field lines are much closer together, in other places they're much further apart. Look at the direction of the field. Think about what the force on a positive charge would be. And if lightning does strike, then it'll be where the field is strongest, and that is the tip of the lightning conductor. So that's the job of the lightning conductor. Okay, in fact, the field is so strong that the air around the tip becomes ionized, and that actually reduces the chance of lightning striking. But anyway, there's another example of a non-uniform field. Charles Augustin de Coulomb, in kind of 18th century, investigated the forces between charges. An experiment very similar to the Cavendish experiment. Cavendish was looking at gravitational forces using a torsion balance, and Coulomb did a very, very similar thing. So we had some charges on balls on a wire that could turn, and then you put another charge close to one of the balls and the wire twists, and by how much the wire twists you can measure the force. And he came up with Coulomb's law. Now, what is Coulomb's law? And there it is. The force between two charges is proportional to the product of the charges and inversely proportional to the square of their separation. In other words, F equals a constant times Q1, Q2 over R squared. The value of this constant is about 9 times 10 to the 9. We actually know now that it's a combination of two very important universal constants, and the full equation is F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. We know pi. Epsilon naught is called the permittivity of free space. There's its value there, which you'll be given, epsilon naught. You can think about permittivity. It's how well an electric field travels through a vacuum. We're going to do a bit more about capacitors, and we'll talk about the permittivity of other materials as well. But free space is a vacuum, and it's the permittivity of free space. It's how well an electric field travels through a vacuum. When we do magnetic fields, there's another quantity, which is how well a magnetic field travels through a vacuum. That's called permeability. We'll meet that later. Okay, but this is F is 1 over 4 pi epsilon naught Q1 Q2 over R squared, and that's basically Coulomb's law as an equation. Here's a question for you to have a go at. Have a read, have a go. Quite a tricky little question, this. So what I'll do is I'll give you a hint if you need it. So if you don't need it, have a go now. Here's a hint. What you can do is work out the tension in one of the threads by resolving vertically, and then resolve horizontally to get the repulsive force, then use Coulomb's law, and the answer is... There you go, and well done if you got that. Now, combining a couple of equations. So we've got F equals K Q1 Q2 over R squared, and E equals F over Q. And if we combine those two equations, what we can do is get an equation for the field strength due to this charged sphere, or due to a point charge. And what we get is big E is 1 over 4 pi epsilon naught Q over R squared. Are you going to have to keep writing down 1 over 4 pi epsilon naught? You know, can you not just abbreviate that to K? And the answer is actually in OCR, no, you can't. You have to write down 1 over 4 pi epsilon naught. They might be generous and tell you that it's about 9 times 10 to the 9. It depends how friendly the examiners are that year. Nevertheless, big E is 1 over 4 pi epsilon naught Q over R squared. Note that the field strength follows an inverse square law. Maybe you did gravitation before you did electric fields. If you did, then you will know all about inverse square laws. You'll know that if we double the distance, then the value is a quarter. If you treble the distance, the value is a ninth. We don't need to know what happens inside the sphere, by the way, so I'm not going to tell you. Here's a little question for you to do. This should be a pretty straightforward one. And the answer is in 3, 2, 1. There you go. Let's just finish by comparing gravitational fields and electric fields. There are other things I could put in this table once we've done the next video, which I will do, but for the moment, just a few comparisons. Now, similarities. So Newton's universal law of gravitation is very, very similar to Coulomb's law. They are analogous. You know, they don't necessarily have anything to do with each other, but if you understand one of them, it helps you to understand the other. So they are analogous. The equations are very, very similar. So F is gm m over r squared. F equals k q1 q2 over r squared. Field strength, little g is F over m, newtons per kilogram. Field strength, E equals F over q, newtons per coulomb. Little g, due to a sphere, is gm over r squared. And here we have big E is kq over r squared. Note I'm being very lazy, just calling it q. So quite a few similarities there. Some differences. Gravitational fields are always attractive. Electric fields can be attractive or repulsive, depending on the charges. There is one type of mass. Okay, there are two types of charge, positive and negative. A point mass would be impossible because a point mass would have infinite density. You could say, well, yeah, what about black holes? They're a point mass. Yeah, forget black holes for the moment. A point mass would be impossible, but we do have these things called point charges. Okay, we imagine an electron, for example, to be a point charge. Whether it is a point charge or not is irrelevant. We imagine it to be a point charge for the sake of our calculations.